Okay, take your attendance first. Okay, class. So let's start our lesson today. So, okay. So last class we did about just introduced about magnetic field, right? Okay. So we go back to the notes. So yeah, we learned about what is meant by magnetic field. Then we learn about how the three field pattern looks like: long wire, circular coil, and solenoid, and three ways how to strengthen the solenoid field by using a more current, more number of turns, and placing a soft iron into the coil. Then we talk about the forces exerted on a current carrying conductor. Okay, so F equals to BIL sin theta was introduced. Okay, and the direction you learned before in your O levels. So Fleming left-hand rule, recall back. So we talked about the unit for magnetic field strength is Tesla. Okay, then I asked you to do this as a homework. Okay, I don't know how many of you tried these questions. Okay, especially number 2. Okay, so use F equals to BIL sin theta. Can anyone get the answer? So number 2 is a little tricky one. Okay, just maybe 2 minutes we spend for this question. The first and third one should be able to. We go to the second one. A wire radius of 0.1 cm can carry a current of 1500 ampere. The density of the wire is 8600 kg per meter cube. In what field must the wire be placed so that it levitates? That is, it floats with no visible means of support. That means you have a wire, okay, carries a very huge current, 1500 ampere of current. It was placed in a magnetic field. Okay, I don't know which direction. It placed in the magnetic field such that it levitates. It can levitate, right? The weight of the wire acting down, mg, it levitates until the magnetic force. We place the direction of the magnetic field such that the magnetic force is upwards. The magnetic force upwards. So we increase the current. Now they say the 1500 ampere is enough for it to levitate. So when it levitates, what equals to what is supposed to write? Of course, the magnetic force must be equal to the force downwards, which is the weight, mg. Okay, this is the first idea must come to your mind. Okay, and the wire levitates. So the magnetic force, because it's a conductor, so this formula must come to your mind. BIL sin theta should be equals to mg. So now the question is what field What field? So they want the field, they want the B. What field can levitate the wire? Okay. So do you have all the informations? Do you have current? Yes, you have current, 1500. L, do you know the length of the wire? Length of the wire is not given. L not provided. L not provided. Theta, because they never mention anything about theta, so we assume the field and the wire is perpendicular. Normally, if they never mention the angle between the magnetic field and the wire, so we assume it's 90 degrees. So sine theta normally become 1. Sine theta become 1. Okay. So mass, do you know? Mass also not given. Mass also not given, but density is given. Density given, radius given. This is a trap. Density was given and radius was given. So how do you use the radius and the density so that you can make as a substitution for the L and mass? Okay, so that's the tough part. Yeah. So B, I is 1500. L we don't know. Sin theta we take 1. Okay, mass, because density given, you change to rho V G. Rho times volume, right? Yeah, density times volume will be the mass, right? Okay, so yeah, so that's one way conversion. Another conversion you can do is 1500 L rho, the volume, right? You can change to length. Volume you can change to length. Okay, because it's the wire, the cross-sectional area multiplied by the length of the wire will be the volume, right? Yeah, so the volume we can convert to L times the cross-sectional area times gravity. Okay. So here we successfully can cancel the L and we make the B as the subject. So rho AG over 1500 will give you the answer. You should get 1.77 times 10 to the power of negative 4 Tesla. The area, of course, is a cross-sectional area. So you have to use pi r squared, right? Pi r squared to find the area. Yeah. So this is how the working should be. Okay. So this is how the bullet trains, right? In Japan, in China now, it moves so fast because of what? There is a magnetic field at the bottom, lift the entire compartment of the train. So maglev, right? We call it maglev, magnetic levitate train. So the magnetic force exert upwards to the train and the weight until the weight of the train balanced by the magnetic force. So it floats on the track. So no friction, so it can move very fast, quite close to more than 300 over kilometer per hour, right? Yeah. Another use of magnetic field. Any questions too? Hope you got the idea. Maybe some of you done this. Good. Okay. Okay, now let's see, move on. Go to the PowerPoint. Okay, there is some examples earlier. You can give a look at the question and answer for your understanding. We straight go to the next part. Force on a moving charge. Okay. So earlier we talked about a conductor carries current, experience force. Okay. Why it experience force? Because actually the current is actually rate of flow of charge. The electron flows. So the electron experience force due to the magnetic field because the electron is inside the conductor. Therefore, the conductor experience force. But actually the force is exerted on a charged particle. Okay. So that's why the definition of magnetic field is a region of space where a moving charged particle, okay, experience force. Okay. So now we're going to focus to, let's say if one electron or one proton move in magnetic field, okay, in a magnetic field, okay. So how the forces will be exerted? What is the formula to use to find the force for this charged particle? Okay. The earlier formula BIL sin theta is used for a conductor. We got current, got length, so that's for conductor. So you look at this diagram. If a moving charge enters the magnetic field, what will be direction of the force acting on it? Okay, the same rule. You have to use the Fleming left-hand rule to find the direction of the force. But there is one problem here. Okay, the charge got positive charge, got negative charge. Okay, you see this diagram here, the first diagram, the first positive charge here. Okay, so you see the positive charge is moving to the left. It's moving to the left. Okay, magnetic field upwards. So use your Fleming left-hand rule. See your FBI, right? Your magnetic field, your index finger pointing upwards. Okay. Your current. Now the problem is the current. FBI current. Current is actually rate of flow of charge, right? The positive charge moving to the left, current is to the left or to the right? Positive charge moving to the left means current is to the left, right? Current follow the direction of the positive charge, right? So if the positive charge moving to the left, that means your middle finger, which is pointing current, point to the left. Okay, point to the left. Okay, so positive charge moving to the left means current is to the left. So by using Fleming left-hand rule, you will find that the force is into the page. Hope you got the idea. So magnetic field is upwards, your index finger upwards. Okay, point now. Your index finger is upwards. Your current, your middle finger is to the left. Okay, and you can see your thumb, which pointing the force is inward. Okay. So positive, no problem. If the positive moving to the left, current is to the left. Positive moving to the right, current is to the right. Okay. But negative charge is the problem. Okay, you see the next diagram here, the next charge particle here, negative charge. Negative charge moving to the right. Negative charge is moving to the right. But if negative charge moving to the right, current will be where? Current is the direction of the positive charge flows, right? If negative charge moving to the right means current is to the left, right? Current is left, right? Opposite to the direction of the negative charge, right? This is the trap here. So if it's a negative charge, current you point opposite direction to the direction of movement of the negative charge. So look at negative charge here. The magnetic field is upwards. Your index finger you will point upwards. Okay. Your middle finger will be on the because current is moving to the right, right? The electron moving to the right, right? So current will be to the left. So your middle finger, you must point to the left. So force still inside for the electron. Okay. So force on a moving charge, there is little trickier. Mainly the negative charge because current will be in opposite direction. Okay. So now we want to get the force formula. Okay. Force on a moving charge. Consider a positive charge moving with a constant speed v at a right angle to the magnetic field. Or flux density B, let's say. What will be the magnitude of the force? So as I said, BIL designed for the conductor. So you see the BIL, because I we know is rate of flow of charge, current, Q over T. And L, we can write in terms of speed times time, right? What is the speed the charge particle travels? So we substitute the I Q over T and L as the VT. Okay. So we get BqV. But this BqV is a formula to be used to find the force exerted on a charged particle if the charged particle moves right angle to the magnetic field. Okay. So, but if the charge enters the magnetic field at an angle theta, okay, then the formula tend to become BqV sine theta. Okay. So you can see this diagram, the first diagram on the left. You see when the V is here, this is the angle. This is the angle theta. It's 90 degrees. So when V is on this side, okay, the one I'm showing you now, okay, coming out of the page. So by using Fleming left-hand rule, we are focusing this as a positive charge, positive charge coming out. So the force will be upwards. But if it travel V like this, the theta is reducing. Okay, the force direction still upwards, but you can see this animation. The force reduces. The magnitude of the force reduces when the angle is decreasing between the V and theta. When the V and the magnetic field same direction, the force becomes zero. There is no force exerted. There is no magnetic force, right? When a charged particle moves parallel to the field line, it doesn't cut the magnetic field line, so it won't experience any force, right? When the charged particle experiences the greatest force, when the charged particle cuts the magnetic field line, right angle, okay, to the magnetic field line, the magnitude of the force it experiences will be the greatest. Okay, so F equals to BqV sine theta. Actually, it obtained from BIL. BIL. The derivation you don't need to know. You must know how to use this formula. F equals to BqV sine theta. So greater the magnetic field, greater the force. More charge the particle possess, greater the force. More faster it travels, the force will be greater. Okay. Okay, this is something very different from fields, right? Okay. Electric field, when a charged particle moving or not moving, it experiences the same force in electric field. But in magnetic field, the force is dependent to the speed. Okay, the only field, the force is dependent to the speed is magnetic field. Okay, yeah, not even gravity, right? Gravity also, whether you are moving or not moving, your weight doesn't change. So not affected by the speed. But magnetic field is affected by the speed. Okay. Okay. Any questions so far? The introduction to the formula BqV sine theta. Okay. So let's move to the next slide. Okay, before we go to this slide, okay, let me go to the whiteboard. I want to tell you something first. Like this. Okay, so that means, let's say this is your magnetic field. The magnetic field, the B. Cross means magnetic field is into the page. Into the page. Okay, into the page. Okay. Dot means out of the page. Out of the page. Out of the page. So remember this sign. So let's say the magnetic field is into the page. Okay. And an electron move into this magnetic field, okay, with a certain speed, okay. Come on, use your Fleming rule, Fleming left-hand rule. Can you identify which direction the electron will deflect? Which direction will electron will deflect? Okay, use the Fleming left-hand rule. Is it upwards 1? Is it down 2? Or is it 3? Out of the page? Out of the page? Or 4 into the page? Which one? Fleming left-hand rule. An electron, electron moving. You can WhatsApp me. 1, 2, 3, 4. All going for 2, right? Down. Is it down? Magnetic field is into the page. Current is to the left, right? Yeah, good. Current is to the left. Current is to the left. So your thumb point down. Of course, 2, right? 2 is the direction of the force. Yes. Okay, so many of you tell me 2. Good. So be aware with the negative charge. Negative charge. Okay, good. So, okay, let me So let's say this now currently at this moment, the electron was at this point. This is a point A. This is a point A. You told me the force is downwards, right? So the electron, what happened? It'll start to move down. It start to move like a projectile movement, right? The force acting downwards. So it tried to curve down. It's curved down. Okay, now let's say the electron is at this location B. Okay, at this location B. The electron at this moment is moving like this way, right? At B, which direction the force will be now? Which direction the force it experiences will be? Is it still vertically down? Or the direction of force also will be shifted slightly like this, right? Do you agree? The force is always perpendicular to the direction of motion, right? The particle move a little tilted down here means the force also will be try to arrange itself until it's 90 degrees to the direction of the movement, right? The force. Because you see Fleming left-hand rule, your all the fingers are located 90 degrees to each other. Yeah. So if this continuous, what type of path the electron will take? If the force is always 90 degrees to the direction of motion, what type of path the electron will take? It will take a circular path. Okay, the particle will take a circular path. Remember, okay. So what is the condition to make a circular path? What is the condition to make a circular path? And the force is always perpendicular to the direction of motion. Okay, the particle will make a circular path, right? That's what you learn in the first topic, right? In circular motion. What is the condition to make a circular path? The direction of the force must be always perpendicular to the direction of motion of the particle. Okay. So, recall back your gravity, your electric field, now you magnetic field. Gravitational field. You launch something, you'll experience what type of path? Parabolic path. Parabolic path, right? What is the condition? The force must be always at one direction, fixed direction. You get a parabolic path. Electric field also you get a parabolic path, right? Same. Because the force is always fixed at one direction. But in magnetic field, the charged particle enters in magnetic field, it experiences circular path. Why? Because the force is always relocate itself so that it's always perpendicular to the direction of motion. Okay, so the force is always 90 degrees to the direction of motion. So you end up circular path. Okay, yep, that's why if an electron enters into a very strong magnetic field, okay, very strong magnetic field, the electron normally will trap inside the magnetic field. It's just circulating in a circular path. It traps. Okay, this is what happens in a magnetic field. Okay, so hope you got the idea.
Sir, can you repeat why the force is acting to the center?
Why the acting to center? Okay, you see this diagram just now? At the point A, you tell me the force is downwards, right?
Yeah.
You go to B now. You go to B. Okay, I go another point. C. Let's say C. C. The particle state going down. Use your Fleming left-hand rule. Check where's your force. So it's going down. The electron is going down at C. So your current is upwards, right? Current is upwards. Magnetic field is into the page. Check your position of your thumb. Is to the left, right? It should be to the left. So any location you use your Fleming left-hand rule, the force will be like this. The force will be like this. So the magnetic force here, is contribute to the centripetal force for the electron, which end up in a circular path.
Okay. Thanks.
Okay. Shakil, got the idea.
Yeah.
Because of your Fleming left-hand rule. So you can see when you turn your index finger a little tilted, your FB, your thumb also will start to change, relocate, right? Always 90 degrees, right? So in this case, the force is always act toward the center, end up a circular path. Okay. Okay. This question, just drawing. So look at this question example. A proton and electron enters a magnetic flux density of 0.04 Tesla perpendicularly. Okay. Both particles travel at the same speed. Okay. Okay. Draw on the diagram the directions of the magnetic force acting on the proton and electron. Okay. So you see in this diagram here, there is two diagram here. Positive is moving a little diagonally downwards. Negative is to the left. Okay. Which direction the force is acting on the positive? Positive is easy. Use Fleming left-hand rule. FBI. B is cross into the page. FBI is to the diagonally to the right. So the force is this way. Correct? FBI, BI, yeah, correct. So force is this direction. And for negative, which direction? Because moving to the left, so current should be to the right, correct? FB is into the page. So force is like this, upwards, right? So the direction of the magnetic force acting on the proton should be this direction, right? Fleming left-hand rule, FBI. Okay, B, what is the magnitude of the magnetic force which magnetic field exerts on the proton and electron? So how much is the force? How much is the magnitude of this force? The formula, of course, BqV, BqV sine theta. Okay. So here we assume that the magnetic field and the direction of the motion is 90 degrees. So sine theta we take as 1. Theta is 90. So just BqV, you can find the force. When you use BqV, the sign of the charge no need to include. The charge, just take it as a magnitude. Just put the magnitude. Okay. Okay. So this how the working should be. So this is the directions and BqV sine theta. Since both proton and electron enter the magnetic field same speed, magnetic force acting on them are the same because they have possess the same charge. Okay. Okay, so we go little challenging. I already told you this. When a charged particle enters in magnetic field, most probably the field is quite strong. It can make a perfect circular path. It's trapped in the magnetic field. Okay. So, because it's trapped in a circular path, what will happen? Yeah, by using a Fleming left-hand rule, you can determine the direction of the circle. You see this up here, negative, or you take the positive, the first diagram, positive charge going up. So current is upward, magnetic field is into the page, thumb must point to the left. So this is your force, okay? So this is magnetic force which contribute to the centripetal force. So you make a circular path, okay? The force will be towards the center of the circle, okay? That's why, in the cloud chamber, in a particle physics, in a cloud chamber, okay, just sorry. Sorry. Okay. So let's say in a cloud chamber, they will apply a magnetic field to identify when a track is what type the charge particle is it positive or negative. Just apply a magnetic field. Okay. Say into the page. If it deviate upwards, then they can predict what type of charge it possesses. Okay. Okay, now tell me. The magnetic field is into the page, applied. A track is formed, a particle is traveling in a cloud chamber, and when a magnetic in moving upwards, can you tell me, this particle, is it charged or negatively charged? Come on, WhatsApp me, or you can tell me here. Is it positively charged or negatively charged? This is your Fleming left-hand rule. Identify for me. The track is moving upwards.
Positive, sir.
So the magnetic field is into the page, right? It's into the page. So one of you said positive, it's positive, right? Because magnetic field is into the page, so B, your index finger, is into the page. Okay, your force is found to be upwards because it's deflect upwards. So the force at the beginning here at this location, let's say we use this point A location. Okay, the magnetic field is into the page. The force, your thumb should be point upwards. So your current is to the right. Your current is to the right, right? So the current is found to be same direction as the charged particle moving. So that means this is a positively charged particle. It's positively charged. Yeah, so it should be a positive charge particle. Okay. So if you have another particle traveling like this, they know this is negatively charged particle. So magnetic fields become very useful in particle physics to identify the property of the particles. Is it positively charged, negatively charged, and more, actually more, not only charge, they can find more. More means by checking the curvature, the radius of curvature, they can find the mass and charge of the particle too. Okay, how heavy it is with checking the curvature. Okay, we will be discussing this soon. Okay. So yeah, so apply Fleming left-hand rule to determine the direction of force. Take note the radius of the circular motion dependent on the speed. More fast it moves, the radius will change accordingly. Okay. So now, unfortunately for you, I think, because this charged particle move in a circular path, now all the questions asked in circular motion will be asked here. So you have to recall back all your circular motion knowledge here. Now they will ask you, what is the radius the charged particle travels? They will ask you to calculate the radius. So recall back your circuit. It's the next slide. That's what it's going to be. Because the charged particle move in a circular path, the magnetic force BqV provides the centripetal force mv squared over r. Recall back your circular motion. What is the centripetal force formula? You learned two, right? mv squared over r. Or what is another formula? mr omega squared, right? Circular motion. So here, if the question asks, what is the radius of the circular path it makes? You have to do BqV same as mv squared over r. So from here, you make the r as a subject. You can find the radius of the curvature. I would say this is a very important equation for you to remember. A lot of things can be asked from this equation. Okay. So the radius of the curvature is found to be mv over bq. That means if the particle is more massive, the radius is going to be larger. Okay. When the velocity is high, the radius is going to be larger. Okay. When the magnetic field is strong, the radius decreases. If the charge is greater, the radius decreases. Okay. Another wrong assumption student will take is if the R is greater, it's greater R, the greater means the particle more deflection or less deflection. Deflection is more or less if the R is greater. Big R. Big R means more deflected or less deflected? Less deflected, right? Remember, and the R is huge means the particle is less deflected. Okay, remember. Okay. So common mistake students do. They think big R means more deflected. Right. Let's say a particle make like this round. Okay, another particle make like this. Okay. So this is a small r. This if this curvature, if you extend it to a circle, okay, the r is so huge. Okay, big r means less deflected. 1 and 2. 1 is less deflected than 2. So remember, big r means less deflected. Okay. So now let's see. Investigate further. So where r is the radius of the curvature and m is the mass of the charge. Okay. So this is another period formula. Not that important, but this is the most important one. Okay. So one example. Okay, let's see. Do together. I give you 2 minutes. Try to explore this question. An electron charge of this and mass of 9.1 times 10 power negative 31 kilogram moves in a clockwise circular motion. A clockwise circular motion. Perpendicular to a magnetic field of flux density of this. A magnetic force of 5 times 10 to the power negative 14 Newton was electron due to the magnetic field. First, draw the circular path of the electron and indicate the direction of the. Okay, come on. So the electron movement is a clockwise direction. Can you tell me the field is into the page or out of the page? Use your Fleming left-hand rule. Find out. This is an electron. Maybe you can select one point here. Maybe you can select the top point. The electron is moving to the right. Can you identify me? The magnetic field is into the page, out of the page. Okay, so one of you said into the page. Into the page, is it? The electron is moving to the right means current. Right? So current is to the left. Okay. So force is definitely downwards because it's making a circle down. Okay, downwards. So force is downwards. So where's your B? FBI. Your thumb is down. FBI. Yeah, it's into the page, right? Your middle finger is to the left. Your thumb is downwards force. So your index finger is pointing into the page. Okay. So into the page is crossing. So the magnetic field is into the page, correct? So that's the first answer, right? Into the page. You just select one point, maybe the top one. You're assuming the electron is moving to the right. From there, that one point can tell us which direction is the magnetic field. Okay. Okay, next. B. Calculate the speed of the electron. So what speed the electron is traveling? They already give all the information. Do they give the radius? Oh, the radius is not given. The electron mass perpendicular to the uniform field density of this magnetic force is this, or force is given. So find the what speed. So magnetic force, given. So magnetic force is BqV, right? BqV. Sin theta, we take it as 1, 90 degrees. So from here, F equals to BqV. We can work out the speed, right? You know the force. Force is 5 times 10 power negative 14. You know the B. How much? 8.2 times 10 power negative 2. You know charge. Charge of electron 1.6 times 10. In the exam, charge of electron, they won't give you in the question. You have to check from the front page of the question paper. The charge is given. So you can find the B, right? So B is F equals to BqV. Then third one. Can you calculate the radius of the circular path? What radius it makes? So how do you start your working for the C? The first statement you must tell what? The magnetic force is equals to the centripetal force. Okay, so this is the first line you have to write. Okay, then BqV equals to mv squared over r. Yeah. Then you rearrange the R, substitute all the information, you can get the radius. You know the mass, right? Mass is given. Mass is 9.1 times 10⁻⁻31. V, you got it from B now. Q, you know, magnetic field, you know, so you can find the R. Okay. So important is the idea. So this should be your working. And this should be your working. So this is your diagram, right? It's into the page. And centripetal force equals to magnetic force, you get the speed. And oh yeah, F equals to BqV, you get the speed. And BqV equals to mv squared over R, you get the radius. Okay. Okay. Okay, so you hope you get the idea. Any questions so far? No questions, Okay, let's continue. Okay, this is the same question as before. You can the same pattern, just using BqV. You can give a try with this later. Okay, the solution is given. Okay, okay. So as I said, deflection of charged particle in uniform electric field, it's going to be a parabolic path. It's going to be a parabolic path. Okay. This is recalling your electric field. Recalling electric field. So if electron up is a positive plate, so electron move up, right? So how do you get how much of force experienced by the electron? F equals to QE, right? Q is in this case we put elementary charge, E, small e. So we can find the acceleration. We can find the acceleration. This is your AS knowledge, right? This is your AS knowledge. Recall. You might think, why suddenly magnetic field? We are talking about electric field here. Okay, because towards the end we will have questions, not little, lots of questions involving both field together. Okay, both field together. So that's why you need to recall the electric field knowledge here. Mainly the force for the parallel plate. Okay. 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 So another one thing you need to know is the differences between magnetic field and electric field. Okay. Try to remember at least 3 differences. Okay, 3 differences between magnetic field and electric field. Okay. So the first difference, the force exerted on a moving charge particle. Magnetic field, the force is on a moving charge particle. For electric field, the force can be stationary or moving charge particle. You will experience force. Okay, the first difference. Okay. Second difference, the force is perpendicular to the both field and direction of motion. Fleming left-hand rule, right? The magnetic force always perpendicular to the direction of motion and the field. Okay, if the magnetic field is downwards, the force always 90 degrees to the field. The force. But in electric field, the force is in the direction of the field, right? If the magnetic field is downwards means the electric field downwards means the electric force will be downwards, right? Yeah, so the one differences. Okay, third one, also unique. The force in magnetic field is dependent to the speed. More faster the charged particle move, more greater the magnetic force it will experience. Right? BqV one. The V determines the magnetic force. But in electric field, the force it does not depend to the speed. F equals to QE, right? It only depends to the electric field strength and the charge it possesses. No V. Another one difference. And recently introduced another one difference is in magnetic field, the charged particle make a circular motion or a arc of a circle. Arc of a circle. It can make an arc of a circle if the radius is huge. The radius is huge. It can't afford to make a full complete circle. It might make just a part of a circle, arc of a circle. Okay. In electric field, you know this, right? It always makes a parabolic path. Okay. Yeah. So remember at least 3 differences between magnetic field and electric field. At least 3. They will ask you in exam. Okay. Okay, any questions from here? Okay, no questions, eh? Okay, so it's a fact to remember, eh? Okay. Okay, these all are same questions, BqV. I just want to go to the whiteboard. I like to ask you one question. You have magnetic field into the page. Okay. Two charged particle. Okay, hold on. Okay, this is a proton. Okay, and another one down here is electron. Okay, enters this magnetic field. Okay, both proton and electron enters the magnetic field with the same speed. Okay, the speed is same. Both have same speed. Okay, same speed. Okay, now the question is, can you draw the pattern, the path made by the proton and electron in this diagram? Which direction you're going to deflect? Okay, and how big is the radius? Okay, come on. Imagine, recall back, proton is more massive than electron. What is same? The speed is same. The charge, of course, possessed by the proton electron is the same. Charge is same. But of course, proton is more massive. Okay, consider that. Can you draw how the circular path is going to look like? Okay, 1 minute for you. Which is going to make a big circle? Which is going to make a small circle? Which direction the circular path is going to be? I use your Fleming left-hand rule and use BqV equals to mv squared over r to predict the r and draw the circle. Okay, without calculating, can you tell me which is going to make a big circle, proton or electron? The heavy particle or the lighter particle will make a big circle? In other words, heavy particle or a lighter particle will deflect less. If it deflect less means it make big circle, right? Deflect less. Which deflect less, proton or electron? Of course, proton, right? Proton deflect less because it's very heavy, very massive. So everything is in the revealed in the radius formula. Make the radius as a subject. R is what? R is mv over bq, right? mv over bq. Yeah. So for proton and electron, V same, charge same. But proton has a very huge mass. It has a very huge mass. So the radius of proton will be very high. So which direction the proton going to turn? Use Fleming left-hand rule, up or down? FBI. Magnetic field is into the page. Current is to the right. So the force is upwards, right? Force is upwards, right? So the proton make a circular path like this. You can draw arc of a circle also, can. So it's make a very big radius. Okay, then how about electron? Electron make a maybe a small circle. It can make a circular. Yeah. Okay, make a very small radius because mass of the electron is very small, and it should circulate downwards because the direction of force is downwards, right? At this moment at the top. Fleming left-hand rule will reveal that, right? Force is down. Here the force is up, right? So proton makes a upper circular movement. Electron is down. The radius of electron is small. The radius of proton is large. How do you know it's large? From this formula. R is mv over bq. Okay. So you have to know what radius to draw, which direction it deflect. Okay, which direction to deflect? Fleming left-hand rule. How big is the R? BqV same as mv square over r. Okay, many different types of question they'll ask. There is question they ask sometimes. What is the ratio of radius of proton over the radius of electron it made? How much? This is a quantitative question. So in this case, of course, radius of proton is what? mv over bq of the proton divided by mv over bq of the electron you have to do. So you have to key in all the mass velocity, you'll get the ratio. Okay, you'll get the ratio. Okay, class. So that's today's lesson. So what you learned today? So we learn about, we go back to the notes here. So we learn about force on a moving charge. We learned this. We found that the force is BqV sine theta. Okay. And we found that it will make a circular motion in the magnetic field or arc of a circle. And we found that the radius it's going to make is mv over bq. Okay, because the magnetic force contribute the centripetal force. Okay, so this is your again your homework. There is some questions here. Use the concept of BqV sine theta to do this question. Okay, the answer is at the side. The next class will be discussing something called Hall voltage. So Hall voltage. Then we're going to talk about something called mass spectrometer involving magnetic and electric field together. Yeah. So after that, just another 2 classes, we can finish it off. Okay. Okay. Any questions? No questions. Okay. Homework. As I said, try to do this question. And go to the slide. Try to do the before Hall voltage. There is some examples. You look at the examples. Look at the solution. Okay. Do first, then look at the solution. Hope you get the same answer. Well, I stop here. Okay. Thanks.
Thanks, sir.
Thanks. Yeah. Okay.
Thanks, sir.
Thanks.
Thanks.